The derivative of arcsin of x is 1 over the square root of 1 minus x squared, which is a standard derivative. But how do we know this is actually the case? So what I'm going to do here is prove that the derivative of arcsin of x is actually this expression right over here. I'm not going to prove it using the limit definition of the derivative, but this means I'll also be assuming that we already know that the derivative of sine of x is cosine of x, which is another proof in itself. So I'm just going to use that common derivative without proving it. So here's what we do. We let y equal arcsine of x. So we would like to find the derivative of y in respect to x if we would like to determine the derivative of arcsine of x. So the first thing to do is to take the sign on both sides, which results in sine of y equals x. Since if we take sine of arcsine of x, sine and arcsine just cancel out and we're left with x. If we apply implicit differentiation and differentiate both sides in respect to x, we get cosine of y times dy by dx on the left-hand side by the chain rule. The derivative of sine of y in respect to y is cosine of y. And we also have to multiply this by the derivative of y in respect to x, which was what we were trying to take the derivative in respect to for the entire sine of y expression. Therefore, the derivative of sine of y in respect to x is just cosine of y times dy by dx. On the right-hand side, the derivative of x in respect to x is just 1, so we have the equation cosine of y times dy by dx equals 1. If we divide both sides by cosine of y to isolate the dy by dx, we get dy by dx equals 1 over cosine of y. So now we have an expression for dy by dx, but we would also like to write this in terms of x. Consider the Pythagorean identity, sine squared of y plus cosine squared of y equals 1. If we subtract sine squared of y on both sides, we get cosine squared of y equals 1 minus sine squared of y. Then we can take the square root on both sides and get cosine of y equals the square root of 1 minus sine squared of y. Notice how this is just square root of 1 minus sine squared of y instead of plus or minus square root of 1 minus sine squared of y. And I'll explain why we can assume the right-hand side of the equation must be positive instead of having two distinct values with the plus or minus sign. So here's the deal. We originally set y equal arcsine of x, and the range of the arcsine of x function is between negative pi over 2 and pi over 2 inclusive. So this implies negative pi over 2 is less than or equal to y, which is less than or equal to pi over 2. Within this interval for y, cosine of y is always greater than or equal to 0, because the cosine function always takes non-negative values in the domain between negative pi over 2 and pi over 2 inclusive. So since cosine of y is always non-negative, this means we can assume cosine of y equals the square root of 1 minus sine squared of y, and it can never equal negative of the square root of 1 minus sine squared of y, which is why we were able to assume this equality without the plus or minus sign. Alright, so if we replace cosine of y with square root of 1 minus sine squared of y using the identity, we have the equation dy by dx equals 1 over the square root of 1 minus sine squared of y. Since sine of y is equal to x, which we worked out by taking the sign of both sides of the equation, y equals arcsine of x, we can rewrite 1 over the square root of 1 minus sine squared of y as 1 over the square root of 1 minus x squared. So this means dy dx equals 1 over the square root of 1 minus x squared. Since we set y equal arcsine of x, dy dx is the derivative of arcsine of x. So the derivative of arcsine of x is 1 over the square root of 1 minus x squared. The proof of the derivative of arccosine of x is very similar, and the result is only off by a constant multiple of -1.